Hello, Professor Siegel. This is our Thermo Project number 2 by Franklin E. Kwandach.
And Tyler Venus.
So the goal of this project was to develop a system that can produce about 100 watts of power or work from a campfire. And then we also wanted to have all of the components for this project to be able to fit inside of a backpack.
So this was our initial concept idea. It all kind of starts with the campfire in the middle. That gives off about 10 kilowatts of heat. And we'd use that heat to heat up our boiler. And then all of our parts of our system are combined with a copper tube. And then from the boiler, it goes connected to the steam turbine. And the steam turbine goes down to the condenser, which we initially had as an ice bucket, but we changed that later on. And then from the ice bucket, it goes back to the water pump. And then the water pump leads back to the boiler. And now for our design requirements, we wanted everything again to be able to fit into kind of like a mid-size backpack. So we were looking for smaller portable parts that could be like packed up easily if we were going camping or something like that. And we also needed the net power output to account for the efficiencies of the generator, the motor, and the turbine, and also make up for the power we needed to run the pump.
So this is our TS diagram. So this is our state point one, which 1 to 2, which is the pump doing work on it, increasing the pressure. And then from 2 to 3, it's going through the boiler where it's increasing the temperature. And then it's going through the state change into a steam. And then here it reaches a dry steam and then goes down to around, we said around 45 degrees Celsius. We thought was a good point where the river water would be able to cool it down to. And then this is our isentropic. You can see its quality is about 87. It's between zero point 0.8 and zero point 0.9, but close to zero point 0.9. And then this is our actual turbine, where our turbine would actually end up. And then it would go back all the way back to state one through the condenser. And then this is our system diagram where we have the pump and the motor. We have pictures of it so you can like actually see it. And then from here, go to the boiler, heat up by the campfire. That's why there's a QN. Then we have state three, where it's a turbine and generator, making that work output. 200 watts, which we will explain why later on. And then condenser, where it's running through a river. Because if you're going camping and you're not near a river, what are you doing? And then back to state one.
Now for the energy analysis. So all these calculations were kind of done to find mass flow rate in the end. So step one, we went to the property table and found our enthalpy and entropy at state three, which was 300 degrees Celsius and 1 megapascal. And then once we had that, we could use S3 to find the quality at state four. So we found our quality.
Go down.
S. And then the quality could be used to find the enthalpy at state 4S. And then once we have that, we could use the isentropic efficiency, which is also the efficiency of the turbine, to find the enthalpy at state 4. That's the real enthalpy at state 4. And then after that, we could find the mass flow rate with this equation down here using the efficiency of the generator and the enthalpies at state 3 and state 4. And also we chose 200 watts because we needed to account for the 48 watts for the pump, but the motor for the pump is about 60% efficient. So that would be about 80 watts. And we already need 100 watts to be produced. So that's about 180 watts. And then we just chose to round up to 200 because it's nice and even. And now for the boiler analysis. So these are the kind of the two main equations that we used. The hoop stress and the longitudinal stress. So in these equations, P is equal to the pressure. R is equal to the radius of the boiler. T is the thickness of the material that the boiler is made of. So we calculated the hoop stress, which was about 75 megapascals, and the longitudinal stress, which is half of that, 37.5. And then we decided to make our boiler out of cold work copper. And at 300 degrees Celsius, cold work copper has 80% strength compared to its value at room temperature. And then the yield strength of cold work copper at room temperature is about 380 megapascals. So from these two numbers, you could calculate that it would have a strength of 304 megapascals. And then from that value, you can calculate the factor of safety, which we got to be 4.05.
All right, and then we were talking about boiler failure, which we need to know the exergy flow. And then for the exergy flow, we use 1 kilogram for the mass because we just thought that would be like a good mass to be able to like, carry around. H3 is the H3 that we found at 300 degrees Celsius and the 1 megapascal. This H0, T0, and S0 are all the dead states. So we just took that to be like the atmospheric enthalpy, atmospheric temperature, which I believe was around 25 degrees Celsius, and the S0, which is the entropy at like regular temperature. And then from this, we were able to find that the exergy was about 837.4 kilojoules. And then since there's 4.184 megawatts in 1 kilogram TNT, we found that it's about zero point 0.2 kilograms of TNT.
So now for our conclusions from the products that we chose for our designs, we think that they would all fit nicely into a backpack, but the tubing to like connect each part might take up a decent amount of space. So we might need to kind of do something about that in the future if we want to improve our design. And also to improve our design, we could think.
And these are the references we use. We have the link to the pump, the link to the turbine, the link to the generator, and the link to the motor that we were using. And then this is the efficiencies of each part. We had about 70% for the turbine, which was also like the isotropic efficiency. Generator had an efficiency of about 85%, which we saw in the energy analysis calculations. And as we talked about, and then these are all the calculations that we did for exergy and all the stress calculations. And that's it. Thank you, Professor Siegel.
Thanks, Professor Siegel.